close your eyes for a moment and imagine this. A massive machine 94.5 meters long with a wingspan of 93 meters. This vehicle takes off from an ordinary airport runway, pierces the atmosphere, reaches the depths of space, unloads its cargo, and returns to land at any airport. No rocket stages, no launch towers, just a single-stage space vehicle pushing the boundaries of engineering genius. This wasn't science fiction. This was the Star Raker concept. So why was this incredible machine never built? The answer will surprise you. In 1979, while America was grappling with a serious energy crisis, aviation giant Rockwell International presented the boldest proposal in history: a single-stage spaceplane powered by 15 engines, capable of crossing the ocean like an airplane and reaching space. The most astonishing part? On paper, this project seemed entirely feasible. By the late 1970s, the energy problem was a dark period for the United States. The 1973 oil crisis had shaken the country to its core. Politicians and scientists in Washington were desperately searching for alternatives. Nuclear energy was controversial. Wind and solar energy were still inefficient. During those years, NASA and the Department of Energy proposed a bold solution: collecting solar energy in space. Solar panels in space could operate 24 hours a day without being affected by weather conditions. The energy would be transmitted to Earth using microwave technology. However, there was a major problem. Each of these solar energy satellites would weigh between 35,000 and 50,000 tons. The Space Shuttle could only carry 27 tons per mission. Mathematically, this was impossible. America needed a much bigger solution. Rockwell International was no ordinary aerospace company. It was the primary contractor for the Space Shuttle. When NASA approached them, they didn't think small. They designed a revolutionary vehicle that would fundamentally change access to space. What makes this story so interesting is that, unlike most spacecraft which launch vertically, Star Raker would take off horizontally, like an airplane. Why can't we fly into space? Why do we have to use rockets that break into pieces? Rockwell asked the same questions, and the answer was Star Raker. Now let me tell you about the incredible dimensions of this machine. It was 94.5 meters long, almost the length of a football field. Its wingspan was 93 meters. For comparison, the Airbus A380 has a wingspan of only 80 meters. This wasn't just a large airplane, it was a flying building. It would have been heavier than all cargo planes of its time and the largest flying machine ever designed. Its triangular wing design and blended fuselage weren't just for looks. They were carefully engineered to provide lift in the atmosphere and stability in space. Its most impressive feature, however, was its cargo capacity. Inspired by the C-5 Galaxy military transport aircraft, the Star Raker's cargo bay measured 6.1 meters by 6.1 meters by 43 meters. This space was sufficient to carry massive satellites or space station components in a single flight. Unlike a space shuttle, it featured a hinged nose that opened sideways instead of a top-loading design. The crew compartment was two-story and featured windows that allowed direct visibility of the cargo area. It was to be equipped with advanced life support systems capable of sustaining operations for up to 24 hours. But there was one thing that truly set the Star Raker apart. Are you ready? It was the revolutionary propulsion system that set the Star Raker apart. Most spacecraft use a single type of engine, but the Star Raker needed everything. Rockwell engineers proposed a 15-engine configuration. These engines were no ordinary jet engines. They were air-cooled turbojet engines. This hybrid system was an approach never before attempted in aviation history. Each engine would operate in 3 different modes during ascent. For the initial takeoff, the turbofan mode would engage. This would continue until the aircraft reached an altitude of 15,000 feet above sea level. Then, the engines would transition to the additional turbojet mode for acceleration. At this stage, the engines could accelerate the Star Raker to 3 times the speed of sound. Finally, the ramjet mode would activate for supersonic speeds. The ramjet engines would demonstrate performance capable of reaching 6 times the speed of sound. During atmospheric flight, each of these engines would provide an astonishing 140,000 pounds of thrust. At 95,000 feet, the air engines would shut down, and at that moment, the true power would kick in. 3 hydrogen-fueled rocket engines would ignite, providing a total of 3.2 million pounds of thrust. Reaching orbit from the runway in a single vehicle was unheard of. But the story doesn't end there. The Star Raker's return would be as revolutionary as its ascent. Unlike the Space Shuttle, which had only one chance to land, the Star Raker was designed for powered flight during re-entry. As it descended from orbit, its massive wings would perform a series of S-shaped turns to control speed and thermal stress. The thermal protection system consisted of 2 different concepts. One was ceramic tiles borrowed from the Space Shuttle. The other was more innovative metal panels with internal insulation. The most interesting part? When Star Raker slowed to subsonic speed, the 10 air-breathing engines would restart. This gave the spacecraft something it had never had before: the ability to attempt a second landing if necessary. Engineers calculated that there would be enough fuel for a 555-kilometer journey after re-entry. There would even be the option to divert to alternative landing sites, a critical feature for a spacecraft operating in unpredictable weather conditions. Rockwell's vision was incredible. A fleet of 30 Star Rakers, each capable of flying multiple missions per month. This meant that a new payload would reach orbit every 8 hours. After a safe landing, maintenance teams would perform basic checks, install new landing gear modules if necessary, load the new payload, and prepare for the next launch. All of this would take place within just 48 hours. Even today, this launch frequency seems ambitious. Of course, creating a single-stage orbital vehicle presented enormous challenges. Challenges that even the most advanced aerospace companies struggle with today. Star Raker would push the boundaries of materials science, propulsion technology, and aerodynamics. In traditional rockets, fuel mass can account for 95% of the total weight. Rockwell engineers believed they had found a solution in a multi-mode propulsion system. Air-breathing engines eliminated the need to carry oxidizers all the way to the upper levels of the atmosphere. The heat protection system also required revolutionary materials capable of withstanding the extreme temperatures encountered during atmospheric re-entry. These temperatures could reach 1,650 degrees Celsius in some areas. Cryogenic fuel tanks had to be light and strong enough to withstand structural loads while keeping hydrogen at -253 degrees Celsius. Now, let's get to the truly amazing part of Star Raker: the economic revolution. Access to space has always been expensive. Reusable rockets such as SpaceX Falcon 9 cost $2,700 per kilogram. During the Space Shuttle era, it was much worse, $54,500 per kilogram in 2011. What about the Star Raker? Just $22 to $33 per kilogram. That's approximately $150 at today's prices. It's not just an improvement, it's a complete revolution. It's like going from traveling between continents by ship to traveling by jet. Star Raker's economy was based on 3 pillars. First, complete reusability. Nothing was discarded. Second, aircraft-like operations. No special launch facilities were required. Third, high flight rates. Development costs were spread across multiple missions. So why was this revolutionary concept never built? The answer is both sad and instructive. As the 1980s began, the energy crisis that had sparked interest in space-based solar energy began to ease. Oil prices fell, and the pressure to find alternative energy sources diminished. NASA's interest in satellite power systems waned as other priorities took precedence. When the Reagan administration took office in 1981, the focus shifted to defense and national security initiatives, such as the Strategic Defense Initiative. Star Raker suddenly became a solution in search of a problem. Technical challenges also played a role. The complexity of a 15-engine system was a major risk. Each engine would operate in different modes, requiring thousands of components to work in perfect synchronization. There were concerns that a single engine failure could jeopardize the entire mission. Materials science was also limited. Today's carbon fiber composites, ceramic matrix composites, and superalloys did not exist at the time. The lightweight yet extremely strong materials required for Star Raker had not yet been developed. Computer technology was also inadequate for flight control systems. Rockwell explored lighter versions and alternative orbits, but without a clear mission, the concept gradually faded away. In 1996, it was acquired by Boeing and never reached the prototype stage. Today, the situation is different. Modern technology can address many of the challenges faced by the Star Raker. Carbon fiber composites can reduce weight by 50%. Advanced ceramic materials provide better thermal protection. Computer-controlled engine systems can increase reliability. Three-dimensional printing facilitates the production of complex components. Today, more than 40 years later, the dream of a single-stage spaceplane still captivates engineers. The British Skylon concept pursued the same goal with its revolutionary Sabre engine, but the company went bankrupt. SpaceX's Starship uses a two-stage approach while sharing the goal of a fully reusable system. Today, SpaceX's Falcon 9 has achieved a cost of $2,700 per kilogram. Blue Origin and other companies are aiming for even lower costs. Star Raker's projected target of $150 no longer seems so far away. As the space economy grows, so does the need for Star Raker-like systems. As we face climate change, Star Raker's original motivation is gaining new relevance. Space-based solar energy is being re-evaluated as a potential clean energy solution by NASA, ESA, and private companies. Star Raker was not just a failure, it was a vision ahead of its time. Perhaps its time is coming again. Looking at Star Raker, it's impossible not to wonder, what if? What if we had continued developing this amazing machine? What if access to space had become more routine in the 1980s and 1990s? Sometimes, even the boldest visions, which seem impossible by traditional standards, are worth pursuing. What do you think? Could the Star Raker have changed the course of space exploration? Was it too ambitious for its time? Or was it abandoned too soon? Share your thoughts in the comments. If you'd like to hear more stories about forgotten aviation projects, don't forget to like and subscribe. In the next video, we'll discuss Boeing's secret design, which was Star Raker's rival, and why NASA chose the Space Shuttle. Remember, what's impossible today may be tomorrow's reality. Star Raker shows us that sometimes our biggest mistakes are the things we don't do.